Section 16.2 line integrals. See the recall? You learned this one in calculus 2. If a force f of x is applied to an object to move it along a straight line from A to B, then the amount of work done is given by the integral. Work is the integral over A to B force. That is the limit of Riemann sums. Here we'll try to obtain work when we try to move an object along a curve rather than straight line. So that's the main application for line integrals. In order to do it more easily or systematically, the curve must be parameterized, and also we'll deal with only parameterized curves in our study. Let's define a plane curve. A plane curve C is given by the vector equation R of t is x of t and y of t. Of course, t is moving from A to B. You can write this vector equation by the parametric equations. So x is g of t and y is h of t in this way. One example of this parameterization is circle example. Then you may define r of t in vector equation, that is cosine t and sine t. And here t is moving from 0 to 2 pi. Then this parameterization will make a whole circle of radius 1. Right? Okay, that is one example. Now also you learned this one when you try to get arc length of curve. Okay. Now delta SI is square root of delta xi squared plus delta y squared, and we get that one. Behind the mathematical derivation is given in this way. That is from A to B, and that is t direction. And now this is curve, so that now that one is transformed this way. This point is over there. And if you consider partition of t, so that we try to use the Riemann sum technique, then for each one in this curve you have a partition like that. So rather than the real length, we may consider here the straight line segment length. So in this case, that is now delta x and delta y, and then that one is now delta s, like that, right? So here, in this way, you try to get this length straight line segment by using the Pythagorean theorem. Okay. So here, divided by delta t squared and outside and delta t, and in the limit we have this one, so that ds is the same as now square root of x prime squared plus y prime squared, and dt. So that is the same as now the length of r prime. So when you try to get arc length of the curve, this is parameterized, then that is now integral over c ds, which is the same as integral over a to b in t domain. Now that is here square root of x prime squared plus y prime squared. You learned this one in calculus 2. Okay. Now we'll do here line integrals for scalar functions in the plane. Here we try to get the w. Of course, once F is force, then W is work, and moving an object along the curve C, and that is the work. And we already know that here ds is same as that one. Now, physically, we may consider in this way. Now, curve is given, then we make a partition so that that portion is the arc length segment for each subregion. We try to get a height, the force magnitude, and summation can be considered. Then that is a Riemann sum, exactly like that one. So delta SI, that is length here, and now height is f of xy here star. That means that these are chosen from the ith portion of the curve, so that this product is summed, which is Riemann sum, and the limit of Riemann sums is defined as the line integral. But behind the application is the computation of work, moving an object by using a given force. Here, f of xy is a scalar function. Okay. With that, behind the physical problem, here we define generally the line integral of a scalar function along C. So we use this notation, and that is the limit of this Riemann sum. And of course, this one is later on will be replaced by that one. We already know that ds is this one. If C is parameterized from T domain, then we'll use this scaling factor. Okay, so here we have formula for this line integral. Now, once C is parameterized from T domain A to B, then the integral is same as integral over A to B, f expressed as a function of t, and that is the scaling factor and dt. So this portion can be written as that one, because originally R, the parameterization, is here now x and y, as these are functions of t, right? Okay, that is the in the calculation formula. By using this formula, we can get the integral. Okay. Evaluate integral over c 2 plus x squared y ds, where c is upper half of the unit circle. Okay, let's try to visualize the curve C. That is unit circle upper half. So it is 1 and minus 1. And that is the curve C. Okay. Now, in order to get the integral, we may have to consider first the parameterization. So it's for C, R of t is x component is cosine t, and y component is sine t. And t is, okay, only upper half, so that t is moving from 0 to pi, right? Okay. And with that, now r prime is minus sine t, derivative with respect to t, and now there is cosine t, so that from here, r prime length is that squared as a sine squared t, and this one squared, so that this is 1, so it is 1. Okay. So the given integral is, by using this calculation formula, the parameterization is from the t is from 0 to pi, and here 2 is 2, and x is cosine t, so there's cosine squared t, and y is sine t, so we have a sine t, and we have to have put here scaling factor, but that is 1, and dt, right? Okay. Now, here we can get this integral separately for this constant, and interval length is pi, so from first one we can get 2 pi quite easily, and plus, and we have to have anti-derivative. Okay, so that must be here a constant times here cosine cubed t. Then this one will make some constant, and if you try to differentiate, then some constant cosine squared, and then cosine derivative will be minus sine, so that if you put here a right coefficient, then that must be antiderivative. Of course, we have to evaluate from 0 to pi, right? Okay, to decide this coefficient, let's try to differentiate that one. Then 3 cosine squared t, and now times minus sine t, so that the extra is minus 3. So we put here 1 over minus 3. Then this will cancel out that 2, right? Okay. So we got the antiderivative, and from here, now 2 pi, and okay, minus 1/3, and then along with the pi, which is minus 1. So minus 1 cubed is minus 1. Once t is 0, which is 1, then minus 1. So that this is minus 2, so that 2 pi plus 2 over 3. That's the final answer, right? Okay. Now so far we considered the line integral over a smooth curve, which has a smooth parameterization. Now, sometimes a curve has many components and not easy to express yet along with one parameterization. For example, a curve can be in this way and another part is like that. Then we may consider line integral. If this whole thing is a C, then we may consider the first part and second part. So that along this part, we try to get line integral, and we do one more along with this one, and then the results can be added to get total line integral. That's an expansion of original definition. So here we try to define a line integral along with piecewise smooth curve. That means that there are n pieces and each one is smooth and parameterizable. Then the line integral over C of the scalar function f of xy can be obtained along with these line integrals piece by piece. First we do piece by piece and then add them. Is it reasonable? Okay, it's quite reasonable, right? Now see this problem. Evaluate the line integral over C 2x ds where C consists of the arc C1 and of the parabola y equal x squared from 0, 0 to 1, 1, followed by the vertical line segment C2 from 1, 1 to 1, 2. Okay, let's visualize the curve. There's y direction, and this is x direction. This is x and y axis, and C1 is along the parabola y equal x squared. Okay, let's try to make this one a little bit better way. Okay, here y equal x squared is coming that way. So from 0, 0 to 1, 1, like that. This is C1. And from here, now vertical line segment. So that is now 2. So it is vertically coming up like that. Right? That is a C2. Okay. The curve C1 and C2 is given, and we try to get line integral of 2x. Okay. So we have to get the line integral separately. Let's begin with C1. So that if we focus on C1, then we have to first parameterize this part. Okay. Now, this is for the parabola y equal x squared. Then if we choose x is t, then y must be t squared. Of course, t is moving from 0 to 1. Right? That's the parameterization. Okay, so here r prime is x prime, that's 1, and that is 2t. T squared is derivative is 2t. So that here r prime length must be square root of 1 plus 4t squared. That's the scaling factor. And integral over C1 of 2x ds is the same as integral. Now parameterization is from 0 to 1, t values from 0 to 1. Now 2x, that is 2t. Now x is t, and r prime, magnitude r prime, which is same as now 1 plus 4t squared, and then dt. Okay, we have to evaluate this one. Now here, for that integrand is half power, so it looks like the antiderivative is here 1 plus 4 t squared and power 3 over 2. Once we can get a quotient, right quotient, then that's the antiderivative. Okay, now after that, we can evaluate from 0 to 1. Let's try to this part. We differentiate this one, then 3 over 2, and this power half, and then this derivative is now 80. So that this one is the same as here, that is 12, okay, 12, and that is square root of that portion, and t. If we compare this portion and that one, here extra is 6, 2 is changed into 12, so that we put here 1 over 6. Then whole, the derivative of this whole must be same as that, right? Okay, so there is an antiderivative for that one. Yeah, from this one, 1 over 6. And then when t is 1, that is now 5, 3 over 2. So there are 5 times square root of 5. And t is 0, then it's 1. So that's a minus 1. Right? So that is the part answer for the line integral. Now let's move on. The second part, C2. We have to get parameterization. But for this one, here x is always 1. So that we may say x is 1 and y is t. But t is moving from 1 to 2. So that's parameterization. So integral over C2 can be here integral from 1 to 2, and then now 2x, x is 1, so 2x is 1. Now we have to put scaling factor and derivative, okay, we didn't do here, but r prime must be 0 and 1, right? So that length is 1, and now dt. So integrand is 2 and length is 1, so that we have answer 2 from second part. So this 2 addition is the final answer. Okay. Now this line integral can be applied for some physical problems, and mass of wire can be obtained along with the line integral once y is placed along a curve C, and with each point density rho, then the total mass must be integral over C of the density. So we can get it. But also, the center of mass of the wire can be obtained along with this one. So that x times rho, the density, and divided by, after getting the integral, divided by the total mass, that is almost the same, in fact, really the same as the computation of a center of mass earlier you studied in this calculus 4. So that is a simple application. Okay. Now let's see this problem. A wire takes the shape of semicircle and upper portion. So it's upper half of the circle of radius 1, and its density is proportional to the distance from the line y equal 1. Find the center of mass of the wire. Okay, So let's see the curve. This is x-axis, and that is y-axis. And, okay, ideally vertical. Okay. Now, we consider semicircle of proportion. That is the curve, and the density is proportional to the distance from line y equal 1. Y equal 1 is this one. That's y equals 1. So that density can be written in this way is proportional to the distance from y equal 1. That is distance 1 minus y. That's the distance. And then we try to use this, the coefficients to express the density. Okay. Now, for this one, to get the center of mass, first we have to get mass, total mass. Total mass is here, same as along the curve integral, and then rho ds. Now, for this curve, earlier we considered that, so that r of t is cosine t and sine t. We can consider this one. Of course, t is moving from 0 to pi, and r prime length is, okay, derivative is minus sine t, derivative is cosine t, the square sum is 1, so that is 1, right? We already did. Okay, so here, that is same as from 0 to pi, parameterization. Rho is now k times 1 minus sine t. Right? And then scaling factor is 1, length of r prime, and tt. Right? Okay, k is constant, and then here k is constant, and for 1, integral is pi. And now for sine t from 0 to pi, the integral is 2. So we obtain total mass k times pi minus 2. Now, how about the center of mass in y direction? So there's a mu y, which is same as integral over c and y times rho ds. Again, if you're using the same parameterization, then integral must be from 0 to pi, and y is sine t. Oops, we have to put here, okay, let's say m times mu y, okay, m times, and sine t, and now rho is k, and 1 minus sine t, and here scaling factor is 1 and tt. Right? Okay, so that now k is constant, and we can put that one outside, and then this integral is from 0 to pi, and sine t minus sine square t and dt. Okay, so here k times this integral is 2, and minus from 0 to pi, and here, okay, we may use a formula for sine square t, which is half 1 minus cosine 2t, right? And then dt. We have that. Okay, this has two parts. One is half, and the other one is half cosine 2t. However, when t is moving from 0 to pi, then 2t is moving from 0 to 2 pi. So that cosine makes a whole cycle, so that halfly positive and halfly negative, so that this will not make any contribution because it will become 0 in integral. Okay, so we have here k and 2 minus, that is half and pi, so that pi minus 2. So that's the integral. So here, from this one, we can conclude the y part, second part of the center of mass is here. What is m? M is now, okay, 1 over pi over 2, but anyway, this is k and 2 minus pi over 2 and over k now pi minus 2, right? So k can be cancelled, and then if you simplify that, or in this way, it will be the answer for the second part. Now, you can do, you can get mu of x, and mu of x must be 0. The reason is, now physically, right now, density is depending only in y direction. As in x direction, they are the same, and this is symmetric in x direction, so that if you try to get mu x, then there must be 0. Of course, here at this position, you are using x, so that is now cosine t, and so that along with this replaced by cosine t, you may keep going, then you will get 0. So that now mu, okay, x must be 0. You can check it quite easily. Okay. Okay. Now we'll continue in the second part. Thank you.